Hi everyone, it's me, Carolyn, and in this video we are going to be looking at um, how we can use the normal curve and what we've learned already on how to work with it to do problems that are very similar to our binomial distribution, especially when we have large samples. And it is basically the binomial that we're doing, but we're going to be using the normal curve to kind of approximate it. So I'm going to share my screen, and I will be bringing pieces to you to kind of remind you of the binomial as well. So it never hurts to remember things. But let's get some definitions down here first. So suppose we have a random sample. So we have a size n obtained from some population where individuals do or do not have a certain characteristics. Now, these individuals could be things as well. So again, that's kind of where we get this binomial feel, because binomial means we have a fixed number of trials. So n would be our number of trials. All of them are going to be independent from one another. Since we have a random sample, they will be independent from one another. And we have two outcomes, either they do or don't have this characteristic. Now, the sample proportion, that's the definition that we're kind of defining here, is this P with this little accent mark over the top. And that's equal to X over N, where X is the number that do have that characteristic that we're looking at. And this will give us some sort of decimal or fraction. So you can kind of remember that P hat. P, and it is read as P hat. So it's kind of like a little hat on top of the P. And this P hat is a statistic that estimates that population proportion P. So it's kind of like remembering statistics are estimates for our parameters. And this time the parameter is going to be our population proportion. Similar to X bar, the sample mean is a statistic for our mean, mu. Okay. For this simple random sample, we've seen these before, some of them anyway, with the size n and a population proportion p. So we already know the p. If the sample is going to be approximately normal, so for the p hat, it's going to be approximately normal, provided we have that n times p times 1 minus p is bigger than or equal to 10. And we saw that in our binomial, and that's when we started talking about how things could be unusual if we were beyond the 2 standard deviations in either direction, because we had that normal, that empirical rule. But we're going to be using the normal curve to do some of the binomial stuff. So the mean of the sample, first of all, that p hat, so the mean of p hat is actually p. And our standard deviation for that distribution is going to look like this ugly looking square root. Now we will be again standardizing things. So we will be doing the data value minus the mean divided by the standard deviation. So we will be subtracting off our mean and dividing by our standard deviation. So that ugly fraction. And I again will be using the table to go through this example. I only have one example with a few pieces because it's similar to what we've already done. So I'm not going to kind of redo things that we've done in other videos. So here's our example that I'm going to work through. And I'll also, as I'm doing this, kind of talk through where the binomial or the steps you would have done if it had been a binomial type problem. A nationwide study indicated that 80% of the college students with cell phones sent and received text messages with this phone. Again, this isn't true data. I guess it would be a lot higher than that because I think most people do send and receive text messages. Anyway, so we're going to get a simple random sample of 200 students that have cell phones, and we're going to look at that distribution. So the first thing we're going to do is just kind of describe what we're dealing with. We are going to look and see what this n times p times 1 minus p looks like. So our n, that's our sample size, is the 200. Our p, that's the proportion in the problem. So that's that 80% that we're talking about. So that's my 0.8. and then my 1 minus the 0.8. If I do the math here, so I'm going to take the 200 times my 0.8 times my 0.2, I get 32. Okay, this number is bigger than or equal to 10. So therefore, thus, we have an approximately normal distribution, which means we can use the normal curve. We also know that our mean of this distribution is going to be that 0.8, that P. I also know that my standard deviation, I'm going to abbreviate here, deviation, is going to be that square root, that's that ugly formula right up here, of 0.8 times 1 minus 0.8 all over my n, which in this case is 200. I'm going to just simplify it a little bit. Just to make things a little nicer. I could get the decimal at this point, but I'm going to let my calculator do all the work when I work through these problems. So here's my mean, here's my standard deviation. And since it's approximately normal, I can use the normal curve and all the methods that we've already talked about in previous videos. And then we can ask ourselves, what is the probability that 154 or fewer of these students in the sample would receive or send and receive text messages? Well, first thing I'm going to do is get our p-hat. Now, p-hat is the number that we're looking at, that 154 out of my 200, which if I do that math, I get 0.77. Okay, so I'm going to draw a picture of what we're looking at. So it is approximately normal, so I've got my normal curve, and the mean is 0.8. I want to know what is the probability that we are less than this. So here's my 0.77, and I want to go less than this. Okay, now if we were doing a binomial, just kind of talking this through, if we were doing a binomial and we were trying to find the probability of less than 154, if we were doing it by hand, we'd have to add up all the values from 0 to 154, because we're going from 154 or fewer. Okay. Yes, we do have technology, and I did show you how to use technology to get that value. So it wouldn't have taken us that long. But in past times when we didn't have that technology around, calculating all of those pieces and adding them all together was a lot of work. So being able to approximate things using this normal curve saved us a ton of time. Because now I can just take this 0.77 and find my z value. So my 0.77 minus the mean divided by my standard deviation, which is that ugly square root thing. And I had simplified it a little bit in here. And now I'm going to get my calculator to do this for me. Okay, so the way I work this, and I've got to be a little bit careful. I have an older calculator, so I'm going to do the top first. So the 0.77 divide minus the 0.8, and I get that value. So right now you can see that negative 0.03. I'm going to go from here and I'm going to divide by, and then making sure to get everything in my square root. So I do have the start of the parentheses. So I'm going to do that 0.8 times my 0.2. And since it is multiplication and everything, I am okay not to put in extra parentheses. If I had addition or something in here, I'd need probably some more parentheses in there. So I'm going to kind of just type that all in and hit my equal button. And there's my negative 1.0606. Again, our z values, we will round to 2 decimals. Simply because that is what my table has. So I am going to be looking here at the negative 1.06. So here's negative 1.0. I'm going to go over to the 6. And I see the 1446. So kind of looking down here, so you can see. So then I'm going to my table. And I get 0.1, I lost it, 446. So that is the probability, because this does tell me the table does go from the point smaller. So that is the probability that I have 154 or fewer. Okay, we're gonna do another one. Actually, I've got 2 more here just for practice, so we see it in all directions, and also remind us how we use the table a little bit. So what is the probability that 172 or more students send or receive text messages? So again, I kind of need to get that p hat that I have, the number that I'm working with, which is my 172 over the 200. I'm going to get that value. So get my calculator out. For my division, 0.86. I like to draw my little pictures. So again, we are working with an approximately normal, or close enough to normal that we can use it. So centered at the mean, which in this case is that 0.8 that they talked about in the beginning. And we're going from 0.86 or more. So we're going this direction. 0.86 or more. And now I'm going to need to standardize that value so that I can go to the table. So again, it's my data value minus the mean of the distribution divided by the standard deviation of that distribution. And I do like to let my calculator do all the work. Yes, some people will put the decimal in there, but if you start dividing by a decimal that has been rounded, that will introduce round off error. And so you kind of want to work with this ugly thing if you can at all. And this formula isn't so bad. There are other ones that we have out there in this statistical world that are a lot uglier. So I am taking that, doing my subtraction, getting that value, dividing it by my square root, putting all this stuff in parentheses underneath that square root. So 0.8 times 0.2 divided by 200. You probably could have done that piece if you had wanted to separately, because I think that turns out to be a nice number. And again, I'm going to round to 2 decimals. So I get 2.12. And then I'm going to take that z value to my table. So remember, the z values are on the outside. The areas are on the inside. And I'm doing 2.12. Remember, this is 2.10. So 2.11, 2.12. So 0.9830. 0.9830. Okay. But that is not our answer, because the table gives us from this point down. So we have to remember that the area under the total curve is 1. So we will be taking 1 minus that. And this is another reason why when you see Excel, and if you remember when we did Excel in the binomial, and we did have that cumulative feature, it always went from that point down, and that comes from the tables that we use. Most statisticians will use the table that we're using or did use at one point in time. I'm sure they're using technology now, but that's why the technology that was created to help us with all these things kind of mimicked the tables that we have. All right, so now I'm subtracting. If I subtract that, I get 0.0170. So the probability that we are 172 or more students get that piece. And remember, this tells us this is unusual. And remembering that terms, and our magic number is 0.05. That's what we kind of set up as an unusual mark. Now, is that always the case of being unusual? Yes, in this world it is, but sometimes we want things to be a little bit finer. So we'll see that in future chapters. We'll start looking at things a little bit differently in the upcoming chapters. All right, I have one more. And here we're talking about more than 148, but less than 180. So again, I'm going to be calculating some pieces here because I do kind of want to put them in my picture. Here's my 0.8. So I need to kind of turn those into proportions as well. So I'm going to take that 148 divided by my 200, and take the 180 divided by the 200. This gives me 0.9. Here, this is 0.74. And now I can put those in my picture. Put 0.74 on this side, 0.9 on this side. I know it's not drawn to scale, but again, it's just to give us a picture of what's going on. Now, if we were doing the binomial and we were doing it by hand, we'd have to do all of our x values starting at, since we're going more than, so we'd start at 149 and we'd end up at 179. So 149, 150, 151, and so forth. We'd have to take all those values and add them together. Or again, using technology has made things a little bit easier. But before that, we had the normal curve. And this is always a nice thing to do, is just kind of refresh our memory on how that normal curve works. So I'm going to find the two z-values. We're taking the data value minus the mean divided by the standard deviation of this distribution. The 0.74 minus the 0.8 all over, oops, 0.9, sorry. Square root 0.8, 0.2, 200, this is my 0.9. Going into my calculator, .74 minus the 0.8 divided by my square root, 0.8 times 0.2. There's my cat. I'm right in the way. Sorry about that. She left a cat there. There we go. All right, divided by the 200. And I get negative 2.12. You can do the 0.9 as well. All these values here, and this is 3.53. And actually 3.54 if I round to 2 decimals. Okay, so looking at my pieces, a negative 2.12, so I'm going to the table. I'll also be taking this step to the table. A negative 2.12, 0.0170. And then I need 3.54. Well, I don't have 3.54 on mine, so I'm going to go as big as I can, which is 0.9998. 0.9998. So we're just going to get as close as we can to the actual values. This would probably almost be about 1, because this is going to be a little bit smaller up here. But we'll go with what we can. So kind of reminding us how we work with this kind of values. Always good to remember, good review. The table gives us from the point all the way down. So this is my 0.9998, actually a little bit bigger. This one here goes from here down. This is my 0.0170. So to find between the two, we're going to take the pink and get rid of this teal color. So we're going to do some subtraction. And I come up with 0.9828. There we go. There's our probability that we're between those two values. Using the table. Again, there is technology that will do it for you. I'm not going to show that to you in this video, just because I do find value in using tables. And sometimes you'll have tables that mean other things. So learning how to read a table is always a good skill as well. I'm going to stop sharing here and bring you back to me. And I'm going to say that we are kind of done with this beginning piece. We will be switching to something a little bit completely different. Again, we will see lots of pieces overlapping, so it's not like we're going to be completely new. We will start to see those formulas again, and things like that. So we'll be using our normal curves. We'll be using a new curve coming up, and lots of other things. But those are in the next videos. So have a great day, and I'll see you in the next video.